Hi, this is the first of 3 looking at survival analysis in SPSS and R. Part 1, we're going to be creating Kaplan-Meier plots and using a Logrank and Breslow statistics. Find more details on my website given below. I'm not going to be giving you details of the statistics underlying the model. That is in my handout shown in front of you, and also you can go to Malcolm Farrow's excellent website on Newcastle upon Tyne. He gives a link in my document to his site. In terms of output, we're going to be looking at 2 main aspects. We're going to be producing a graph called the Kaplan-Meier graph, PL graph for short, which shows survival over time. It's usually produced as the most important aspect of any survival analysis and reports. And then we can produce a model. The model shows the relative risks for various independent variables we might consider. These are called covariates in this area of research. The most important thing to notice is that we're dealing with data that has censored observations. That is, the observations don't suffer an event, and a certain proportion of them are still alive at the end of the trial. It might not be alive or dead, it could be discharged and still sitting on the ward or anything like that. Let's look at some data. Here's some data concerning 19 patients who had stage 3 diffuse histiocytic lymphoma in 1976, a long time ago. So we have 19 patients here, and it has survival time in weeks. Notice that these are ordered from smallest to longest. You don't need to do that, and obviously a data set might not be in that order. I've just done that to show you what's going on. And then we've got here in the second variable which shows their status, whether they completed the trial, 1, or whether they were censored observations. Now this is important to realise that when we're talking about here completed, we mean they died, and when we say censored, they're still around. So if you count them up, you'll notice that we had 8 died and 11 survived. So we've got 11 censored observations out of 19. So we have more than 50% of our patients are still alive. Although that's a good thing, it's a bad thing in terms of statistics, because we can't know how many will survive for. As you can see here on the graph, we have this data represented over time, and what it does is move every single value to the beginning, so we catalogue everyone who survived for that length of time and then gradually moved onwards. Notice the dashes represent the censored observations, and as you'd expect, there's more censored observations as the time would get longer. Now let's produce this graph in both SPSS and R. Here's our data in SPSS. Let's have a look at the variable view quickly. So we have survival _t, which is the time of survival in weeks for each of our subjects. And then we have the event variable, which has 2 values. 0 equals censored, 1 equals completed. Remember, completed means they died in this instance. Back to the data. We see this in order to say that doesn't have to be at all. I've just done that to make things easier for you. And we can see there those that suffered the event and those that haven't. And we can click on the tabs, the labels viewer, to see if it's what they actually mean, those values. To carry out the analysis, we go to Analyze, Survival, Kaplan-Meier. Analyze Survival, Kaplan-Meier. Then we take survival _t, put it in the time box. Status, we know that's the event. Click on event. If you remember, the actual event is 1, so we put in the value 1 there, say continue, and that's it. Then we say OK, and we have a graph at the bottom of the output, which is exactly the same as described in the handout. The actual calculations are given above. How this table is calculated again can be found in the handout, and also there is a mean estimate plus a 95% confidence interval. But with the high level of censoring in this data set, it's not really of much use. Sometimes we wish to graph more than one survival curve on one plot. basically to compare. We might have 2 or 3. Here I've added some more data to our tumour group. So we can see to case 19 that we had before, I've added a grouping variable here. I've classed them as group 1. I've added a second group. This second group actually consists of a number of observations from people who had stage 4 tumour instead of stage 3. So now we have the same thing, a set of survival times, and those that died, indicated by the 1, and those that survived or censored, whichever you want to call it, 0. So we do the same thing again to draw the Kaplan-Meier graph. We go to Analyze, Survival, Kaplan-Meier. Put in the survival time, the event, and remember we coded 1 as died, which was classed as the event, and we add what's called a factor. Our group variable represents the factor. Click on Options to make sure we get actually a survival graph. Continue, and OK. This time we get a little table at the beginning telling us the total number in each group, 19 or 60, number of those that died in each group, and those that didn't die in each group. So we can see that the number of those survived in stage 3 were 57.9% compared to stage 4, which were 25%. So it looks like your survival rate is much better for stage 3, but remember why we're using this analysis is because we're talking about censored observations as well. So we might have a large number of people that joined the trial at a very early date and they've died, whereas the other group might have had a much later access to the trial. There's a table which I say is explained in the notes, and here are the mean confidence intervals and the median confidence intervals for stage 3 and stage 4. Notice stage 3 doesn't have a median confidence interval, and we'll see why when we look at the graph. Here is our graph, and basically the median survival time is when the cumulative survival tip function equals 50%. We can see for our stage 3 there is no 50%. They don't ever make it down that far. We have a much higher survival rate than 50%. So we can't work out a median survival time for them. And you can see here straight away that there's a great deal of difference between the two groups. What would be nice is to actually have an inferential statistic to tell us what the chances that these two survival curves come from the same population. And we can do that quite easily. To get the inferential statistics, we call up our dialog box again, the Kaplan-Meier one we had before, and you'll notice here that it says compare factor. Click on compare factor and we've got the option for 3 tests. My notes describe what the differences are between them. Basically the Logrank test considers the curves equal over the length of time, as the Breslow gives more importance to the earlier observations, the shorter lengths of time of survival. So we'll choose both values, click continue and run it again. And there, now we find we've got an additional table called overall comparisons. So we've got the Logrank test, which gives us a p-value of 0.01, and the Breslow test, which gives a value of 0.02. So you can say that once in 100 times we would get a sample that would produce 2 survival functions like this from a population, or a more extreme difference. Or if you wanted to take the test approach, you could set a critical value, say a 0.05, and say we're prepared to accept that they do come from the same population if the value is greater than 0.05, and we say that they do not come from the same population if it is less than 0.05. This is less than 0.05, therefore we would say they are statistically significantly different. Before we start analysing the actual data in R, I'd like to just mention the type of data I'm going to import. I exported the data from SPSS to a tab delimited file, and it's given the extension DAT, but it's actually tab delimited when you choose save as in SPSS. So here is the resultant file with the variable names at the top and then the values all the way down to the bottom. They're divided by tab characters, that's why it's called a tab delimited. So to import this into R, we simply use one command. We say file equals file.choose, open close parentheses, comma, header equals, then capital T. Why I put header equals capital T is because the first row consists of the names of the columns. So the first row consists of the names of the columns, and we want that to be known when it imports the data. Choosing this option here, file equals file.choose, brings up with a dialog. We can just find the file rather than typing in the whole path of the file here, which often you can't remember. And then we're going to put the data into my cancer data. So if we press return, we get the usual find file dialog box. Then we find our file and carry on. You don't see anything unless we type in the actual data frame we created, noting that the first row is made up of data, not the names of the columns. Now to actually produce the Kaplan-Meier plot in R, we simply follow 5 commands. So first of all, we've got to make sure we have a library run in R which is called survival. So we type in library survival and it loads it. I've loaded this already, so there's no message. Normally you get a message saying file library loaded. Now what we're going to do is create a survival object. This is necessary because it's a particular type of data structure that R understands to carry out the survival analysis. Here we are. So what we're doing is using this magical term called serve with a capital S, and then we're saying we're going to use survival time variable there. If I had attached to my data set, I could just put in serve underscore t, but it means I haven't. I've actually put the data set name and then the field name, the same, data set name, and then the field name, which identifies the event. And then we put in those into a survival object, which is called my cancer serve. We can see what this looks like simply by typing my cancer serve, and there we are. Notice that it presents it as a set of observations that are completed or censored. Now what we want to do is actually put that survival data object into a Kaplan-Meier object. So to do that, we use this thing called serve fit. We're saying fit survival function to our survival data, which we defined there. And we don't want a constant interval. Actually, it still produces one in the table, even if we say no, but it doesn't on the graph. We'll see later on. So we're putting all that into my cancer serve KMS. Basically, I'm thinking that in my mind as my cancer survival Kaplan-Meier estimate. Press return. Again, we don't see anything unless we type in the name of the object we just filled up. There we are. And it tells us what we've got in 79 records, number of events, that's the percentage that died, etc. And the median survival time. Remember, we're looking at all the values here. Before in SPSS we actually carried out this simple analysis just using the stage 3 tumour group. We can actually obtain the table of the survival functions for each time, just as we did in the SPSS output by using the word summary here, except it needs to be in lowercase s. There we are. and there's the table, pretty much the same as we got in SPSS. Now what we've done all this for is to be able to create a plot of this Kaplan-Meier object, survival times. So we just say plot my Kaplan-Meier survival estimate, press return, and if we search we'll see it's behind there. Click on it and there we are. Notice this is the whole group, 79 subjects, not just the stage 3, so we do get the survival curve that goes below 0.5, and again the lines represent the censored observations, which become more and more as the time goes on. To produce a graph with 2 lines, i.e. for stage 3 and stage 4, we modify our curve fit function. This is what we had before. Now I want to change that, so actually we have an independent variable with 2 levels. So to do that, just slightly modify it. So here we have now, and there we are, the group is the independent variable, and we know that takes the value of 0 and 1. Now we want to plot this. Before we just simply typed plot and then my cancer serve KMS, and we've got the plot. This time we want to actually modify the plot slightly so we can get some more detail, change colour and provide a legend. I'll just show you quickly what it would look like if we didn't do that first. Now looking at the plot, we can see we've got the 2 lines. We can't tell which is which really. There's not different colours, not different thicknesses, there's no legend, there's no title. We actually want to create all that now. So to do that, use the plot command again, but we add a lot of extra detail to it. So this time we type plot, comma, and then we leave it open, press return. That gives us a plus sign and says, oh, you haven't finished, what more do you want to add? So we say, first of all, we want to say the line thickness is going to be 1 and 3 for each of the lines. Similarly, we carry on, and we want to say the colour of the line is going to be blue and red. So colour equals blue and red. Now I want to give our x-axis a label. I'm going to give it a label, survival time days. Finally, I want to give the actual Kaplan-Meier graph a label. So we say survival histocytic lymphoma stage 3 and 4. Press return. Now if we go back to our graphics window, we have the 2 different coloured curves. It'd also be nice to add a legend to it, so we can do that as well. So we say the legend is positioned where x equals 10 and y equals 0.2. And the legend has 2 labels in it, stage 3 and stage 4. Notice again we've left it so it doesn't complete. There's a bracket missing, so if we press return we get the plus sign again. We can say we're going to show what the colours are of each of those. There we are. So we're saying the colours are blue and red, and the thickness of the lines is 1 and 1. Let's return. Now go back to the graphics window, and we have it. You'll notice that I made a slight mistake there. They're both full thickness straight lines. Whereas if you look back here, I said 1 and 3. We need to do there was probably say 1 and 3 as well. That could be a little exercise for you. You might want to actually save this to a Word document. You just simply go on File, Copy to Clipboard, and it's probably best to copy it as a meta file if you want to be able to enlarge it or resize it in any way, or even edit it. You can also save it directly as a PDF file or a JPEG. To produce the same inferential statistics we did in SPSS, we use this command, serve diff, and then we put in our survival object, my cancer serve, and then our independent variable, the grouping variable, and we use this thing called row equals 0. Row equals 0 gives us the Logrank statistic, 0.0109, which is almost identical to what we obtained in SPSS, 0.011, and then we change the row value to 1 to produce a similar statistic to the Breslow statistic produced in SPSS 0.022 compared to the one in SPSS, which is 0.027. It's slightly different because R uses a slightly different method to calculate this statistic using what's known as the Petro modification. More details in my handout.